in a small room and do the presentation. I think you see the screen as well as you hear our voices. Let me start. As you saw, the program will be mostly about our capabilities, what we're doing within our battery testing lab. And this is the work, I have to say, not only from me, but there is a whole team behind it. And these are just the three main people I would like to mention here. Priscilla Caliandro, who's really our electrochemical backbone, basically, as a co-managing director of the BFH Center. Together with Christian Oxenbein and Bruno Lemoine, as senior project manager, working since 2021 here in our lab. So I mentioned the BFH Energy Storage Research Center. We are situated at Switzerland Innovation Park BLBN, just right behind the train station in Biel. And the idea of the BFH Energy Storage Research Center was that we wanted to concentrate, the Bern University of Applied Sciences wanted to concentrate all its research groups on electrical chemical storage technologies in one single location, coming from different departments as well as different research groups to cover basically applications as well as technologies within this topic. And it started in 2014. And we started 2014 basically in the same configuration as we are now. We are covering 6 fields. One is testing and characterization. Then we use basically the knowledge we get from testing to apply energy storage in mobility application or in energy system application, together with PV, for example. We have a group looking at manufacturing technologies for lithium-ion cells. They have a nice facility also in Burgdorf. We have also a smaller fuel cell test bench, and we're working together with economists and data scientists who are looking at basically innovation ecosystems. Today, I'm mainly going to talk about the, now we should see, the battery and storage system lab. So basically about testing and characterization, and really want to show you in the first part of the presentation what tests we are doing, what can we actually offer, and why do we these tests. And in the second part, we're looking at algorithms which we develop based on these tops, on these tests. So basically here you see again the whole value chain which we are covering with our battery and storage system lab. We do a lot of testing with our infrastructure I'm going to talk about. These tests are then used to basically create models of our batteries. We're using different methods to make models, simpler electric circuit models or more complex physics-based models. And these models are then actually used for algorithm creation, for state of charge, state of health, or state of function. And we also have then the facilities to implement these algorithms into hardware and do the software validation basically on our test bench we have also. This work is actually, since a long time, one of the core activities here at Bern University of Applied Sciences. It started very early on. Actually, I did the first battery test bench in '93 for the solar car racing here at Bern University of Applied Sciences while I was still a student. But when I started actually as a professor here, we did a lot of advanced battery systems for quite crazy applications like glider planes or electric bicycles, which are today, as you can see here, mainstream. And as you can see also, the applications evolved over the years. It went more industrial applications like forklifts, buses, trains, trucks is a very hot topic at the moment. And with the development actually of the markets and our partners, we developed also the technologies and the areas which we were working. When at the beginning, it was more about electronics and battery management systems. We started more and more actually working on algorithms. And finally, also, as you can see here, since about 2 years, we're working in machine learning algorithms, which we implemented on a open source battery management system. This is actually a quite complex overview, but as you can see, basically this is the story of the BFH Energy Storage Research Center, which was founded in 2014. And we are really heavily relying on infrastructure, which we invested a lot, and especially in 2021, we moved from our old place to a new place and increased our capacity twofold. And we're using this infrastructure to develop, on one side, more test algorithms, as well as then in the last 5-6 years, more models, including now, as I said, machine learning. As you can see, there's a lot of funding involved here from different sources, being it European or Swiss. And we actually also put a lot of effort into communication. For example, also as the PhD summer school, where we have a dedicated slot for batteries. We're partnering with iBAT, and the last large project with a lot of partners is Circubat. And as you can see here, always we had some demonstrators, being it buses, trucks. This is a portable battery for construction sites. We converted an Audi A2 into a pure electric drive car, and there are some partners which we're working on. So I was talking about the battery testing lab. You can actually later on click on the presentation here. It would open probably here. It doesn't work because I'm on the laser. Yeah, I have to switch back. But anyway, it's not important. But you can have a 3D virtual tour of the of our lab. As you can see here, we have quite a nice infrastructure, lots of thermal chambers as well as testers. If we look at the systems we have, we're heavily relying on aspect temperature chambers as well as PEC as our system testers. They are quite powerful because they have for each channel for cell testing about 50 amps, and we can then put them in parallel so that you can run tests up to very high current limits. As we have 3 racks with 40 channels each, we're 120 channels, and a total, I think, of 13 temperature chambers, 7 large ones with over 1,000 liters. And we also have some battery management system, hill testers, where we can actually test algorithms of our battery management systems. Now, let's look at what kind of battery testing we do and what you can actually read out of it and why you should do it. It starts very simple one. It's characterization. As we can characterize, I would say, it starts with small cells, as you can see here, 18650 cells, where we have the infrastructure to test a large number of these cells in parallel. Or we can also, as you can see here, this is a structure where we can use pouch cells. And as you can see here, we're connecting, I think, about 6 or 7 of the channels. So that's running a test at 3 to 400 amps. We do tests where we actually look at charge and discharge curves, as you can see here, for different temperatures. As you can see, the impact of the temperature on the capacity, for example, also for different C rates. As you can see here, these are then different C rates. We measure the voltage, very high precision, as well as temperatures. And then we can give, for example, for a given temperature, the discharge curves for different C rates and see the impact on the available capacity. And finally, also, as you can see, we can see the impact on temperature. This is a very special battery. As you can see here, normally you're not able to charge a standard lithium-ion battery down to -40 degrees, especially not several times. But you see the impact actually on the low temperature at -40 degrees. Out of that, actually, not only characterization of the curves, but we're looking at what is basically the power map, you would say. So what is the internal resistance map of a cell? So that's something which you can see is typically dependent on the state of charge. Here is the charge current, here's the discharge current. As you can see, it's quite logical that if you have a very low SOC, then you can charge the battery with very high currents. As you can see, this is again temperature dependent, but basically it's possible, at least for higher temperature, to charge the battery up to 400 amps. If you then have more and more state of charge. So it means when the battery is almost full, then as you can see, the charging current decreases. Why is this actually important? Power maps like this are actually used in inverters or in battery management systems, which tell the inverter in a drive system what is the available maximum power out of the battery. You can do then the same thing for the discharge, and there is exactly the other way around, as you can see here. If you have a very low SOC, then you can have only small discharge or smaller discharge current compared to very high SOC. Basically, this translates to a resistance curve, as you can see here, again, for different C rates and as a function of the SOC. The way how it's done, you see a little bit of on this side here, you run at different SOCs, you run basically charge and discharge pulses. You have to slightly increase every time the pulse to see if you're still within the possibilities of the battery. As soon as then, for example, for discharge, the battery hits at the end of a 30-second pulse, the lower value of the end of discharge voltage, then you have to actually stop. So it's a little bit trial and error. And another testing capability we use often is drive cycles. Now this sounds very automotive. As you can see here, it's a conventional automotive drive cycle, like the highway profile or US profile, which we use to see the distance we can go with a car. But we also have drive cycles for electric trucks, or as you can see here, we always support two Formula E. That's actually a Formula student. Yeah, sorry. That's Formula student teams. The one from ETH Zurich does the tests at our lab, as well as the one from Bern University of Applied Sciences. What is special here is that they're racing actually 15 CP currents, and that you also have to be able to do. And we are actually on our test benches. So what is also important is basically aging. After performance, most of the questions customer have is about aging. And there we actually make the distinction between two effects. One is cycling aging. So how fast does the capacity, the available capacity of state of health decreases over the numbers of cycles, as well as calendaric aging. So basically you do nothing, you just store the batteries and see from time to time what is the available capacity left. Again, here you can see we do these tests. For example, what is the available capacity if you discharge the same cell with 100% depth of discharge, so from 100% loaded down to 0 at 25 degrees 1C, or if you would only run it between 80 and 20 degrees, so that's less energy per cycle measured. But if you then look at the SOH and the numbers of cycles you will get, there's a higher amount of energy turnover you can get. So, and for calendaric aging, it's actually important to see what is the state of charge where you actually store the battery, and then you can actually get very important storage or calendaric aging behavior. We do a lot also aging tests of intermediate diagnostic cycles. So we basically run the batteries with certain predefined cycles, but then from time to time we do diagnostic cycles. The diagnostic cycles allow us actually to look, we can then make an OCV curve, for example, where we see that the OCV actually is over age will change, and that's something which you can take into account into your battery management systems, especially in your algorithms. We also look at incremental capacity analysis, see how this moves over the number of cycles. So you see here that the capacity per change of voltage is decreasing over numbers of cycles. So that's also an indicator of aging. And we do also, when we do these diagnostic cycles, we look at electroimpedance spectroscopy, and we'll later talk about this as a very good tool to see what happens inside the battery when with the numbers of cycles. Again, you can see here basically the characteristics or the impedance changes. We do long-term tests. As you can see here, on top is calendaric degradation tests. As you can see, the number of hours here, this is a test which was run over a year. And from time to time, as we said, we did these reference cycles. And these are same battery, but for different types of state of charge for storing. And there you can see actually what is the impact of, in this case here, it's the temperature impact. Here is the average SOC or state of charge impact. As you can see, if it's fully charged here, it's actually decreasing much faster than if you have an average SOC of 20% in this case. Or you can... this is 45 and this is 20. And yeah, that's for different temperatures. And then we have here very long-term cycling degradation tests. As you can see here, again, also what is the depth of discharge and the average SOC influence, or then the C rate influence. So these are quite intensive tests and gives you a good idea about the aging. What you can get out of it is basically curves like this, which you can then implement basically in your models. So the impact, so if this is the linear slope, so the more negative, the faster the battery actually is aging. For example, here's the temperature. So you hit on this x-axis, so you see here, if the temperature is around 25 degrees, it's almost zero, but with high temperature it will also age a bit faster. The average SOC has also an impact on calendaric aging. So basically, if I look at these two curves, the best thing is to store at 25 degrees and at an average SOC almost 20%, so that's almost discharged. And the same thing, you can then see what's the impact on cycling capacity degradation slope. So here you see temperature. We know that this is like an inverse bathtub curve. So there's an optimum temperature, so somewhere around 25 degrees. If it goes lower, then there's aging. If it goes higher, there's aging too. So this is general knowledge, but we actually do these tests because for each battery there is specific data you want to get, as well as for the impact of C rate or the impact of depth of discharge or the average SOC. So now I will give actually the word to Priscilla, and she will continue to show you on how you can accelerate these tests.
Yes. So we just saw that it's possible to do quite exhaustive characterization of lithium-ion battery in terms of cycling and calendaric aging, but there also might be another way to perform lifetime estimation with Coulombic efficiency measurement. This test actually is comparative, so it means that generally the outcome that you can get out from a Coulombic efficiency measurement is a comparison among different cells, and how it is done is generally you should charge and discharge your battery with constant charge, constant current charge, constant current discharge, and integrate the current over time to get the capacity that you are storing inside the cell and the capacity that you are getting out while discharging. In case the ratio between these two quantities is equal to 1, actually it means that you have a perfect cell, and you won't expect degradation. But generally, if you have an instrument that is capable to measure these two quantities with high precision, with 5 decimal, up to 5 decimal, you can quantify what are the parasitic losses that are occurring inside your battery, and so kind of understand which is the batteries that has the lowest losses. So this is just an example that we get it out from literature, and they were comparing 5 cells. And here you see the Coulombic efficiency measurement, and here you see the SOH. And now you see, for example, that if you would only consider the capacity degradation, you see that battery 1, okay, was the best, but battery 2, battery 5 and battery 4 was comparable after few few hundred cycles. But Coulombic efficiency measurement already up to the 16th cycle was giving to you a ranking in which it was saying that actually the cell number 1 was the one that was having the lowest losses. So it was the one that is most likely to have the longest lifetime. That actually is what, in the end, the experiment kind of prove. So generally what you would like to have is to perform those measurements. You need to have a high precision tester that can quantify this variable, and you want it to have the value of this capacity ratio closer to 1. And actually, this is one of the tests that we perform in our laboratory, and here we just reported the normalized capacity fading after 2 days of 2 batteries, the red and the blue, we will say here. And at the beginning, it seems that, for example, the red battery was performing a bit better of the blue, but looking at the Coulombic efficiency measurement, actually the blue battery was closer to 1 than the red one. And if we kept going after 20 days, so up to it was actually high fast current charge and discharge. We saw that actually the blue outperformed the red one. And without doing those tests, actually already at the beginning, we could say that with Coulombic efficiency measurement, only with few cycles, we could say that the blue one was most likely to outperform the red battery in terms of life cycle expectancy. And this was done on cylindrical cell. So Andrea already said that generally while we are performing this degradation study, electrochemical impedance spectroscopy is a very valuable instrument in order to monitor degradation. For example, here it's a test that we have performed in our laboratory in which we have cycled our cell and getting regular impedance spectroscopy over the time after number of cycles. And you see that actually the shape, the Nyquist plot is changing over time. And generally we see that this part of the diagram is not changing while this part is changing. So since electrochemical impedance spectroscopy is calculated, so is recorded over frequency, generally the frequency spectra is indicating what are the elementary phenomena that are occurring in the cell. So generally from a Nyquist plot, in which we have reported also in a test that we performed here in the laboratory, a fresh and aged cell, from a Nyquist plot, we can perform a distribution of relaxation time that is a convolution technique in which we can express as peak the elementary phenomena that are occurring in our cell. And for example, in this case, we observed that at high frequency part, actually the spectra was not changing much. And the degradation phenomenon that we are observing due to the aging is due to the mid frequency part that is mostly related, for example, to cathode phenomenon, so to positive electrode. So it means that in this case, there is a passivation layer or other phenomena that are occurring in the cathode that are ruling our degradation. So we don't only do cell testing, but we also do module testing. We have 2 equipment to test module, and generally we have the possibility to control the BMS over CAN with our testers so that we can impose switching condition based on the weakest cell of the module. This was an experiment we were running over some months in which we were checking, for example, what it was the effect on a load cell that was inserted in the module when it was built, on the preload force that was imposed in the module, generally to keep the swelling of the cell into a reasonable limit. And we saw that actually over the cycling, since the battery was swelling a bit more and was building up pressure between charge and discharge, the load on this spring were increasing. So these are things that people should take into account whenever they build up their module so that they can adjust time by time what it is the preload force that they have to impose on their battery module. Another kind of test we were performing, it was also here about degradation, and we were also checking with infrared camera the hotspot in our battery pack, for example. And also in this case, we were performing some diagnostic cycle to keep track of the degradation of the module through a full equivalent cycle, as well as not only capacity decrease, but also power fading in terms of internal resistance increase. Now we move to the battery modeling part. So this was everything we could offer in terms of testing, and now we switch to model. We have a quite good portfolio of available model in our laboratory, and yeah, you can see in this plane between accuracy and CPU time that the model kind of position differently in this over these two axes. And what we can offer generally as BFH is equivalent circuit model up to fully physical based model. The two of them have pro and cons. So, for example, the equivalent circuit model are very fast generally to compute, but they lose a bit in accuracy, while physical-based model, they are very accurate, but also quite CPU intensive. And lately, since 2 years, actually, we started a group in which we are working on data-driven model that can actually have be a very good compromise in terms of accuracy and CPU time, since those models actually run quite fast and they are very accurate. Lately, we also work on to International Energy Agency Annex on a model that actually position themselves here into this accuracy to CPU time coordinate, and we call it Open Sesame Battery, and I will explain it a bit later. These are the activity that we have performed towards the year. So this was a work in 2019 in which, one of our students, Daniel Luder, that now is in Aachen University and doing his PhD, he performed a model, an equivalent circuit model, in order to compute the SOC of the battery and have a very accurate result. So what he used, it was an equivalent circuit model that was complemented with a Kalman filter model. The model, in order to be parameterized, actually needs quite some testing in order to understand which are the elements of the circuit. So what it is the value of the equivalent circuit that we need to impose. And by actually testing the model towards drive cycle that have quite a lot of dynamic, so it was possible to see that the model is able to estimate the SOC of our cell with an error that is generally, the mean is low as 2% error on the SOC estimation, and generally we never outgo the 6% error. In order to increase actually the estimation capability of the equivalent circuit model, Dani always supervised under our supervision. He put himself into the BAT physics-based model. So we actually have in-house a fully based physical-based model that in which even here, so we always have to do some experiment. And in this case, actually the experiment will also complement it with microstructural analysis, since our physical-based model needs also to take as input data related to the microstructure of the cell, something like average radius of the particle or void fraction, so that we can input those microstructure model together with performance indication, for example, OCV or drive cycle, to perform parameter identification that will fill the model, as well as we use those tests in order to validate the model out of our experimental measurement. Actually, the model is very complicated and cannot be solved generally on BMS because it requires to solve differential partial equations, so a combination of differential partial equations. And what it was done is actually to simplify the model into single particle model and even more into state space representation, so that actually it was possible to use this space microlab box together with the Texan Instrument Launchpad, so to implement the state space model into a microcontroller, so that almost what you do with the BMS. And in this case, actually, we saw that the model was outperforming much more the equivalent circuit model, and the error was, the maximum error, actually, it was below the 2% in terms of SOC estimation. Why it's so important to have a physical-based model, you were wondering. And actually, it's because if you have a physical-based model that is expressing internal state variable, like, for example, solid potential or electrolyte potential or electrolyte salt concentration, actually, you can perform, for example, fast charging, not into a restricted voltage range of SOC, but maybe you can outgo and do fast charging even at high SOC, but still be able to stop the fast charging whenever you know that the electrolyte potential or the solid state potential is going into a state in which we know that lithium plating will occur, so that we can stop the fast charging into a safe region, so to minimize degradation, but still be able to do fast charging also at high SOC. Now, moving from SOC model to SOH model, this was another work that we have done with our student, and it was a probabilistic approach to SOH. So it means that this was done for the Swiss Trolley Plus model project, and what we have done is 3 years of testing, extensive testing in terms of cycling, and all this testing that we have performed, we have collected the data into a probabilistic approach. So say that we have a certain C rate, a certain temperature, given the multitude sample that we have tested, what it is the probability density function that our cell can perform a certain number of cycles given our operating condition. And actually the model was created in order that if you if you have as input an SOC or a power profile, and you perform rain flow algorithm that can divide your cycle into sub-cycle, you can attribute to each sub-cycle a probability of this cycle to perform a certain number of cycles, or in other words, what it is the degradation that you can get by performing this small cycle and computing over the full SOC profile over the time. You can get actually here, for example, the estimation on how many bus the S trolley bus can do before end of life. That in some case was as high as 200,000 cycles to street. So here we have the Open Sesame battery that we have developed together with CSCM in the framework of the International Energy Agency energy storage group work. And the Open Sesame battery model is based on two models, so a battery dynamic model and a battery degradation model. It's actually open source, as you can read from the title. The battery dynamic model, it takes in consideration a very simple equivalent circuit model with a resistor that is varying with respect to operating condition, but also with time. And actually, so yes, by having the open circuit voltage and this impedance of the cell, we can get out the voltage of the battery in any operating condition, as well as the SOC is updated every time with Coulomb counting. Together, the battery dynamic model is complemented with the battery degradation model, in which we can compute, given an SOC profile and the degradation model that is based on stress factor. Again, one. Yeah, so the stress factor, we can compute calendaric degradation and cycling degradation, so that the model can give us an output, capacity, and power fading. So how it is structured, the model is actually very flexible. It had a very good software architecture, and it is divided in different blocks. So we have as the input block, in which we take into account as input load and temperature profile, and other parameters. For example, what it is the stress factor for a certain battery. Actually, we can see it after into the simulation core. Okay. That you have the possibility to transform the load profile in an SOC profile. So everything is already programmed inside. So it really means that you are flexible in the input that you can give, and all the other transformation is happening into the simulation core. And actually, in the simulation core, you can also have this chemistry library, in which we implemented already by default 3 chemistry in our model that are NMC, LTO, and LFP, based on data that we have acquired experimentally in our laboratory and that we have double-checked with literature actually. And also we are working on a thermal battery model that will complement this simulation core. And the output will be that you will get a structured result in terms of key performance indicator, for example, full equivalent cycle and SOH or SOR, state of resistance, towards, so with respect year or full equivalent cycle. And here is an example. So actually you can find the Open Sesame battery model at this link, or maybe just access it with this QR code. And here is the two, the output that was mentioning before, capacity fading and power fading with two respect, so cycling and calendaric. So you will have the contribution both from calendaric and cycling. And you can test it. It's, I think, straightforward to use. This is the machine learning part that we started in 2000. My God, it's very late, right? Or not?
That's okay.
Okay. We started 2 years ago, let's say, in which we had quite 4-year data on 12,000, almost 13,000 batteries that we were able to analyze. And they were from an electric bike that actually is the fast electric bike in the market. The battery, it was a 20 ampere hour cell with 18650 cell. We got those data that were not the perfect data set, but it was really good in order for us to start with this activity. In fact, by just analyzing the data and analyzing the number of cycles that we had available from this battery, we arrived to a number of cycles that we were able to analyze over 1 million, so 1,200,000. What we have done with this data is that we have performed machine learning. So first of all, we have to clean the data and transform the time data, for example, into structured time data, for example, drive cycle data. And we have applied long short-term memory architecture that is a neural network application in machine learning to get some model out of these 13,000 battery. And if you see here, the true SOH is the blue curve here, that it's of one specific battery over total capacity, so capacity throughput. And we see that actually this battery has a resolution of 1% SOH. And the orange one, it's the model, how is the model able to predict the SOH of one battery? That has a very good agreement. And what we were also able to do, based on the model that we have found with machine learning, it was also to propose operating strategy that allow to the battery to increase the lifetime. For example, in this case, this was a battery that was always being charged 100% and was never used fully. So it means that the user was just using 50% of the available capacity, but every time that it was stopping, so was finishing its usage, it was always going back to charge at 100%. And we know that this is detrimental for the battery lifetime. So what we say is that generally we can propose to fleet owners or customers operating conditions that are better for the lifetime. And for example, here we say, okay, what it will happen if we just charge maximum to 80% SOC? We see that actually we can increase the lifetime of almost 5%. And this is just, you arrive to 85% after,
25% total.
20, So out of this drive cycle analysis, we actually came up with the idea that we could do machine learning with much powerful tool if we would allow to store in the BMS directly time data, not as time data, but as statistical. What do we mean? So look here, for example, we have temperature variation over the year. So, and we know that in winter temperature is colder and in summer temperature is higher. And also that we have starting SOC always that is 100% and maybe that we are finishing our drive cycle at a certain SOC. So we have depth of discharge and cycle duration. So our idea was that why should we store the time data while we can store it in much more compact way, and so that the data are already kind of pre-processed in a statistical form. So it means that on the BMS, we can, at a specific time, we can record histogram like depth of discharge, depth of charge, SOC at the end of charge, SOC at the end of discharge, C rate and temperature, and have a picture that is describing our battery at different time. And not only is describing our battery at different time, it's also telling to us what is the history of this battery. For example, we know that, we might know, it's okay. We might know that, for example, a battery has been used mostly in the low temperature region, so that we can say why the SOH is decreasing that much, it's because actually the temperature was too low for this usage. So here you have some of the advantage of having the statistical data frame. So you can store the data directly into the system. It will serve as a battery passport mostly. The connection to the cloud can happen on demand or periodically or by service. So you are not forced to store to be connected to the cloud. And so the data are stored over the whole lifetime of the battery within a single parameter. So actually the storage space that you need will never change. It's always the same histogram that is actually increasing the count. And most importantly, the pre-processing step is already happening on the BMS. So it means that you save a lot of time and you can directly go and apply the machine learning. I think you can go here so that you go faster.
Okay, so for the finish now, some projects, just some pictures. The e-dumper has been widely published. I think we did actually apply, for example, the Coulombic efficiency measurement to decide between two types of battery cells which were available at that time and which were used to build then at this time, largest battery in a electric car. And this vehicle is still running close by here to our center. Then Swiss Trolley Plus, we've been involved. That's where we actually applied our statistical state of health model. And this is actually still used by Hess to plan the size of the battery of their buses depending on the circles they actually have to, or the lines they actually have to drive. And Swiss Trolley Plus, by the way, is really a successful project for Hess. They sell it quite a lot here, also in Switzerland. And the third application is the application of our, how can I say, the prediction of lifetime using Open Sesame tool, where we were actually working together in a project with SBB. Where we looked at integration and management of batteries and rail vehicles. So they're going to convert quite a lot of their vehicles into electrified vehicles. And so they will save a lot of diesel consumption. But the question was, could we actually use some of these batteries for additional services like power stability, grid stability, or day-night shifting? And one of the works we've done there first was basically identification of the energy profiles, looking at different places. So you could see that, for example, here in Lucerne, you would actually have quite a lot from the grid and not as much from the battery. That means that for the shunting, basically, which would happen here with SBB in Lucerne, has lots of electrified overhead line, whereas in Sion, you would take quite a lot of the energy from the battery and not so much from the grid. So that's also an indication of how this battery would be charged versus this battery here. So there's different types of availability of the batteries, because when they're connected to the grid, you can use them as additional storage. Based on that, and then using Open Sesame, we were looking at the input of the charge rate, basically, on the aging, till we get an SOH on 75%. And there were different profiles actually involved. And really with this, with the tool Open Sesame, we were able to actually predict that it would be better. And that's one of the outcomes here, to actually use lower charge rate than a higher charge rate. So whenever you're on the grid, go with lower charging power than with higher charging power. And it depended also actually a little bit on the station, as you saw some of the places where SBB were using these locks, they didn't have a lot of time, so they would have to actually have a higher amount of charging power, which would reduce the lifetime. And there you see actually we did the same thing, because Open Sesame offers an NMC model as well as an LTO model, and you will see that for LTO the difference would not be as big as for NMC. And the good thing is actually that because with SBB a lot of these things are pre-programmed, there's quite a lot of predictability actually in the operation of this batteries. So you see here the state of charge during the day. when does what happen? As you can see here, typically in the afternoon, in the evening, there would be a lot of shunting actually happening, and that's where the SOC would change. And you would do this over a season as well as over a whole week to see how this behaves. And based on
Priscilla, I can still see you moving, but Andrea is frozen.
Battery, sorry, that's the last slide, by the way, Christian.
Okay.
Okay, but you hear us, huh?
Yes.
Yes.
Sorry?
I could not hear you for some time, but okay. No.
Can you hear
That's
us?
good. Yeah. No, I don't hear Andrea.
Just half of.
But go now.
Oh, no, okay. Now I'm working with the, okay.
Okay.
Yeah, sorry. So this is the last slide anyway, and then we switch over to the microphone of Sheila. And we are actually, what we see here again, instead of running the battery, always charge at 80%. You run it at roughly 55, then charge it just before you will use it, and then dislodge it again. And with this, we actually could reach an increase of lifetime. Okay. You run it at roughly 55, then charge it.
I think it's good.
I think now you should switch to your. Okay.
Yeah, it seems something created some problem here at the end at the last slide before everything looked good for me. I don't know if it's just for me or if the others had the same problem, but I think, yeah, thanks for the presentation, Priscilla and Andrea. I think we can open for question. You can raise your hands or write directly in the chat, and we still have some minutes to use. I have to find which one asked. That's Marcel Held. So Marcel Held, please ask your question.
Yeah, hello everybody. I have a question to Priscilla concerning the Coulomb efficiency.
Yeah.
You said you have measured this at 35 degrees C. What is this temperature? Is this an environmental temperature, a cell temperature? How critical is temperature for this type of measurement?
It is critical. We would like to have a temperature that is the most stable possible. What we do is that we generally have active cooling, so we can fix the set point of our temperature chamber. So the measurements are done inside temperature chamber, and we monitor the temperature of the surface of the cell. And mostly important, we apply a low C rate, so that actually the cell is not heating up too much while performing those kind of measurements.
Okay, but what is the variation you see in temperature during these measurements?
Less than 1 degree.
Okay.
It means you really have to have low C rates. Huh? You cannot, you know, this test takes a long time basically because by your testing you cannot, as soon as you have too high currents, then you increase the temperature internally.
Yeah, okay. Okay, thank you.
Thanks, Marcel. Is there somebody else that has a question here? Yeah, well, that's Beat Ruhstaller. Hello.
Hello. Hello. Thank you very much for a very interesting overview presentation. I have a question to Priscilla about the impedance spectroscopy data. You've indicated that for that certain cell that you analyzed, the mid-frequency range indicated some degradation of the cathode, right? Is this just specific for that type of cell, and which cell was that?
So it might be specific, but generally what you have to do in order to understand first which are the phenomena that are happening, it's very important to kind of perform kind of a sensitivity analysis in which you are sure that you are alterating, so that you are, I don't know how to say, but yeah, that you are touching specific phenomenon. So if you are, for example, a time-dependent effect, for example, conductivity is temperature dependent. So by changing the temperature, you see that the peak is moving, so that you are sure that you can say that this peak is temperature driven, while temperature is not affecting, for example, diffusion. So you know that it's not transport limitation, that it's affected by this peak. So there is a study behind, there is a sensitivity analysis that can allow you to confidently say which peak is attributed to which phenomenon.
Okay, yeah, I understand. Thank you.
Yeah, thank you for the very interesting question, Beat. And we are still before 5 o'clock, so there would be still a chance for 1 or 2 questions.
It was quite a speedy presentation. We had to. There's 2 questions.
I'm sorry if there's someone else. You can take someone else first.
Okay. So Stefano, you want to start first?
Yes. Thank you very much for a very nice presentation. I have a question for Andrea. Generally, you are performing tests on standard lithium-ion batteries, and also you said also with fuel cells. Are you aiming to performing tests on solid-state batteries? Is this a topic for for you, or is this an upcoming project soon?
I would call this as a wish. We would like to have some solid-state batteries available, and then we would test them. That's for sure.
We already did the kind of this prototype from Axel.
Yeah, but that's really one thing. But yeah. we try to get our hands on some solid-state batteries. It's not as easy currently, but as soon as we can get, then we will certainly look at it.
And maybe, yeah, we have temperature chamber that can go up to EUCAR level 6. So it means that it's still,
I think we're not limited in that sense from the testing side.
Exactly.
Yeah. Okay. Thank you very much.
Yeah, thank you, Stefano. So we go back to Beat.
Yeah, sorry, just another question came up. You introduced this current efficiency measurement. It's a very valuable method, and I understand that the accuracy of determining the current efficiency is crucial. So you need specialized equipment for that. May I ask you, did you use commercial equipment, or you developed some hardware yourself?
No, we didn't develop hardware. We are using the commercial equipment. And actually, what is really important is that, we need to have a certain accuracy into the voltage measurement, because actually we need to be very precise whenever we do the switch voltage in between charge and discharge. And also that the time sample at which these voltage points are taken, it should be the lowest possible. So the smallest time interval possible, because if you actually would switch the voltage from charge to discharge a bit low, a bit after that we have the switch voltage, the Coulombic efficiency, so the computation of the capacity over times will not be such accurate, and it should be as accurate as 0.01%.
I think there are some very good publications by Jeff Dance about the required accuracy, and then we did benchmark our test benches versus the published data, the requirements basically, and then we saw that we are basically we're playing in the right league. We are also one in case of voltage, because we have these 3 different resolution levels on a very good level. So yeah, we're confident that we can get some good results.
But we can say batteries are getting better, so it's more difficult, right, than some years ago. The Coulombic efficiency is higher than before, right?
But it's really a benchmark test. This we should stress. So it really can give the comparison among cells.
Yeah, I would say that too. We are very confident to say which cell is better than the other.
Yeah.
but making prediction on the numbers of cycles you can reach has a certain non-security level. So we always recommend for a fast beginning to Coulombic efficiency, but then for really getting a better idea, then do a calendaric and cycling test.
Okay, thank you very much.
Yeah, so it's 5 o'clock. If not, somebody else would have a last question, and otherwise I would stop the recording and would say goodbye from here on, and I hope to see you on June 28th in Biel for the circular economy workshop. Would be great to see you there, and otherwise in 1 month when we have TSC Trollerage. So see you there. Thanks a lot, everybody.
Okay, bye-bye, and thanks for everybody for listening in.
Thanks. Bye-bye.
Thank